So hello and welcome to today's concluding discussion of stoichiometry. So, how many grams of water can be produced when burning 12 grams of propane in the air? So, how much of this do you get if you use that? It's stoichiometry. And the first step in any stoichiometry problem is balance the equation. Propane, the other reactant, of course, burning in the air, is O2. That gets us carbon dioxide and water. One protein requires 5 molecules of oxygen. You get 3 molecules of carbon dioxide, 4 molecules of water. Next step is go to mole. 1 mole of propane weighs 44.09 grams. That gets us moles. Next step. Third step in any stoichiometry problem, of course, is mole ratio. 1 mole of propane produces 4 moles of water. And the last step in a problem involving stoichiometry is go to units. Get the answer in some usable form. In this case, it wants grams of water. So 1 mole of water weighs 18.02 grams. So 12 times 1 times 4 times 18.02, that's everything on top, divided by 44.09, divided by 1, divided by 1, that's everything on the bottom, 19.61805,398. Started with 3 significant figures. The weights both have 4. The mole ratio, of course, is perfect. So 3 significant figures, 19.6. Grams of propane cancel grams of propane, moles cancel moles, moles cancel moles, and we're left with grams of water. Simple. We'll try another one. How many grams of water could be produced by reacting 20 grams of sodium carbonate with 25 grams of hydrogen bromide? Again, the first step is balance the equation. Sodium carbonate and hydrogen bromide produce sodium bromide, water, and carbon dioxide. One sodium carbonate requires 2 hydrogen bromides. You get 2 sodium bromides, 1 water, and 1 CO2. Next step. Second step in a stoichiometry problem is to go to moles. 1 mole of sodium carbonate, 2 moles of sodium at 23, 1 mole of carbon at 12, 3 oxygens at 16 each, gives us 105.99 grams per mole. Next step. Third step in any stoichiometry problem is, of course, our mole ratio. 1 mole of sodium carbonate produces 1 mole of water. And our last step, go to units, and it wants an answer in grams of water. So 1 mole of water, 18.02 grams. So 20 times 1 times 1 times 18.02, that's everything on the top, divided by 105.99 divided by 1 divided by 1, that's everything on the bottom, 3.400320785. We started with 3 significant figures. Both the weights have either 4 or 5 significant figures. The mole ratio, of course, is perfect. So 3.40. Grams of sodium carbonate cancel grams of sodium carbonate. Moles of sodium carbonate cancel moles of sodium carbonate. Moles of water cancel moles of water. And our answer is 3.40 grams of water. And is that the final answer? Well, no. And why not? Well, the question is how much water can you make from 20 grams of sodium carbonate? And the answer is, of course, that you can't turn sodium carbonate into any quantity of water. You can't change sodium carbonate into water. You can't transform the elements. You can react sodium carbonate with something else and have water be one of the products, but you can't change sodium carbonate into water. Well, we have something for it to react with. We have the HBr. And so we can change all the sodium carbonate and react it to produce water, right? Well, maybe. And why maybe? Maybe because we only have 25 grams of HBr. And is that enough? Well, why is that a problem? Well, in the previous problem, when we were burning the propane in the air, we didn't worry about how much oxygen we had, and why not? Well, we said we're burning it in the air. The atmosphere of the Earth provides virtually an unlimited quantity of oxygen. It is inconceivable that we could be burning enough propane to use up all the oxygen in the atmosphere. And so no, there was never any question about running out of oxygen in running that reaction, in burning a limited amount of propane. That's not the case here. We have a limited amount of sodium carbonate and a limited amount of hydrogen bromide. And the question becomes is, do we have enough of everything to actually run the reaction or not? Well, how can we tell? Well, we have 20 grams of the sodium carbonate. We got 25 grams of the HBr, so we got more of it, right? Well, not necessarily. And why not? Well, we said mass doesn't usually tell us what we want to know. We don't care how much, we care how many. The fact that we have a greater mass of hydrogen bromide isn't telling us anything. Everything weighs different amounts. 1 gram of one thing is an entirely different quantity than 1 gram of something else. And so just because we have a greater mass of hydrogen bromide doesn't mean we actually have more of it. And so, now what? Well, it's straightforward. We're going to have to do the same calculation, and now we're going to have to do it for the hydrogen bromide as well. 1 mole of hydrogen bromide, 1 mole of hydrogen at 1 mole of bromine at 79, gives us 80.9. So 25 grams times 1 mole divided by 80.91 is moles of HBr, and we end up with more moles of HBr. Sodium carbonate is heavier, and so the 20 grams is fewer moles. So do we have more than enough HBr to run the reaction? Well, we not only have a greater mass of it, we have more moles of it. But surprise! We actually need more moles of it. We use up the HBr twice as fast as we use up the sodium carbonate. So the fact that we actually have more HBr doesn't in fact guarantee us that we have enough to react all the sodium carbonate. We're going to have to go through and finish the calculation. So, 25 grams of HBr times 1 mole divided by 80.91 grams of HBr. 2 moles of HBr produce 1 mole of water. 1 mole of water weighs 18.02. Multiply through 25 times 1 times 1 times 18.02 divided by 80.91 divided by 2 divided by 1. 27839577484. We started with 3 significant figures. The weights both have 4. The mole ratio is perfect, so 2.78. The grams of HBr cancel the grams of HBr. The moles of HBr cancel moles of HBr. Moles of water cancel moles of water. We're left with grams of water, so 2.78 grams of water. And so what's the answer? Well, are we going to add the 3.4 to the 2.7? Are we going to get 6.18 grams of water out of it? And the answer, of course, is no. Because we're back to our original question. How much water can we make out of 25 grams of HBr? And of course the answer is again none. You can't change HBr into water either. So no, we are not going to create 3.4 grams of water from the sodium carbonate and 2.78 grams of water from the HBr. We're actually going to produce one or the other of those quantities. And which one are we going to produce? And the answer is we're going to produce whichever one is less, in this case the 2.78 grams. And why? Because having produced 2.78 grams of water, we'll have run out of HBr. And what happens to a reaction when you run out of one of the reactants? And the answer, of course, is it stops. So having made 2.78 grams of water, there's no HBr left. There's nothing for the sodium carbonate to react with, and therefore the reaction will halt. So we talk about a limiting reagent. The limiting reagent is the reactant in lowest stoichiometric amount. And the important word in that definition is, of course, stoichiometric. It's not the one you have the fewest grams of. Like we said, mass doesn't tell us anything. Having more or fewer grams doesn't mean you actually have more or less of that material. And it doesn't mean the one you have the fewest moles of. In this case, we have more moles of HBr, but we need more moles of HBr. We use it up faster. The limiting reagent is present in the lowest stoichiometric amount. Not the smallest number of grams, not the fewest number of moles. The lowest stoichiometric amount. Simply and straightforwardly, it's what you run out of first. Because once you run out of one of the reactions, the reaction is over. And with that, we have come to the end of Chapter 3. You get started on Chapter 4 next. Go and have a nice day.